some of them cannot come today. So it's a pleasure to have Professor Zeilberger, and I can't quite repeat your title. Something about...
the joy, I'm going to talk about the joy of dreaming to be famous. Okay. Many people dream to be rich. That's why many people every week buy a lottery ticket. If you are a rational agent, if you are purely rational, then it's a stupid thing to do, because it's a known fact that the expected gain of a lottery ticket is negative. You have a small probability, maybe 1 in a million, of winning a large sum, maybe $1 million. So the expected gain is will be 1, but the lottery ticket normally costs maybe $2. So you lose. But the emotional gain of buying a lottery ticket is positive, because dreaming to be rich keeps you going. Your life is so miserable, your life is so boring, and that's the dream of being rich. Even if it's a tiny probability, will keep you going. And of course, every week you check the lottery ticket and you failed. It's a little bit disappointing, but it's always next week. So there's always the hope that keeps you going. So do buy lottery tickets, but don't overdo it. If you, instead of lottery, go gambling in the casino or the stock market, you can develop a gambling habit, and this may not be a good idea. So it's okay to gamble because it keeps you going, but within reason. We mathematicians do not care about being rich. If we cared about being rich, we could have gone to Wall Street and gotten a lucrative job and gotten much more than we get as mathematicians. We do care to be famous or immortal. So our dream is to be famous, to prove a famous open problem, a famous conjecture, or to disprove a famous problem, open problem, or famous conjecture. So in addition to my day job, doing the old boring stuff that with 95% chance is going to succeed, and I have yet another mediocre paper in yet another mediocre journal, and then I can list it as a list of publications. I invest a tiny, not a tiny, maybe 10% of my time trying to prove the Riemann hypothesis, trying to prove the Goldbach conjecture, and some other lesser famous things. And I think, within reason, it's a good idea to gamble. But like investing in the stock market, you have to be wise and clever. You have to have a mixed portfolio. Of course, it'd be great to prove the Riemann hypothesis. It'd be great to prove the Goldbach conjecture. It'd be great to prove that P is not equal to NP. But frankly, the probability that you will prove them is very, very small. But in addition to the super famous problems, there are semi-famous problems that get you semi-famous. So you should also think about those semi-famous problems in the time allocated for long shots. And in this talk, I try to describe some of my favorite famous and semi-famous problems that I hope one day to either prove or disprove. As a matter of strategy, disproving is usually easier than proving. To prove, you have to prove it for everything, blah, blah, blah. For example, to prove the Riemann hypothesis, you have to prove that for every zero of the Riemann zeta function on the critical line, the real part is 1/2. But to disprove the Riemann hypothesis all you have to do is use the computer and come up with an n0 such that the real part of n0 is not 1/2. And you also probably get $1 million that the Clay Foundation offers. Of course, people already tried this, and if there is a counterexample, it's very, very high. Andrew Liskor and his colleagues at Terriel went very, very far. So I think for the Riemann hypothesis, it's a better bet to try to prove it. So let me tell you about another problem that I believe is not as difficult as the Riemann hypothesis, because it hasn't been open so long. The P is not equal to NP. And later on, I will describe how to formulate it in such a way that almost everybody can understand. What I like about problems is, my favorite problems are problems you can explain to a high school kid or even elementary school kid. Now this you can easily explain to a high school kid. And the Riemann hypothesis you can also explain. This is a formulation that I will shortly tell you about the Riemann hypothesis. So let's start with conjectures. A long time ago somebody called, and sometimes it's easy to disprove conjectures. So usually to disprove a conjecture is easier than proving it. So Fermat, a very, very good mathematician, made the following observation: 2 to the power 2 to the power 1 plus 1 equals 5 is a prime number. 2 to the power 2, it is 17, is a prime number. 2 to the power 2 to the power 3 plus 1 is 257, is also a prime number. 2 to the power 2 to the power 4 plus 1 equals 65,537, is also a prime number. So he said it's very reasonable, since all these guys are prime numbers, that for every integer n, is a prime number. But less than 100 years later, maybe 100 years later, Euler proved that 2 to the power 2 to the power 5 plus 1 is divisible by 664. And nowadays with a computer, you can do it in 1 second, and you don't have to be an Euler to disprove Fermat's conjecture. Even Fermat could have easily spent 1 afternoon to disprove his own conjecture. All you have to do is do it mod 641. And by doing repeated exponentiation, you can easily, so you just look through all the primes up to 641 and do repeated approximation. In 1 afternoon, I challenge everybody, without a computer, without cheating, I'm willing to bet in 1 hour you can disprove Fermat's conjecture, what Euler did. That's by repeated exponentiation and do it mod things by paper and pencil. So here's an example of a famous conjecture. There was a stupid conjecture by hindsight. You cannot generalize from 4 cases. It's like the old joke about the mathematician, physicist, and engineer. The physicist said, the mathematician says, 2 is prime, 3 is prime, 5 is prime, 7 is prime, hence every odd number is prime. The physicist says 2 is prime, 3 is prime, 5 is prime, 7 is prime, 9, an experimental error, 11, 13 is prime, hence it's prime, everything is prime. And the engineer says 2 is prime, 3 is prime, 5 is prime, 7 is prime, 9 is prime, hence every An odd number is thing. But of course, they're all stupid. You cannot jump to conclusions. In this case, so let me first tell you about the big guys. The Riemann hypothesis. The Riemann hypothesis is usually formulated in terms of complex analysis. You define a function by an infinite series and say it converges for the real part bigger than 1. Then you say there is a homomorphic continuation, blah, 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 and then you talk about the zeros. But you don't need all this heavy machinery. You can explain the Riemann hypothesis to a smart elementary school child. It's well known and not too hard to see that the Riemann hypothesis is equivalent to the following counting problem. You count primes. How many primes are they less than n? So Gauss famously conjectured that the number of prime numbers less than or equal to n is asymptotically n over log n. Meaning, and counting prime is easy, and okay, a high school kid knows about log n, number of digits. So this means that there is some constant, such this goes, this is little o of n. And all the Riemann hypothesis is claiming is equivalent to the following. That the error is like this, n to the power 1/2 plus epsilon. For every epsilon, the difference, the error terms between the number of prime numbers less than n and n over log n is like this. If you prove this, you get $1 million. But even this, we know so little, will make you famous. Nobody has any clue how to prove that there exists a constant, capital C, not depending on n, that this is true. We know so little. So this is the Riemann hypothesis. Another equivalent formulation is in terms of the Mobius function. The Mobius function is 0 if n is divisible by a square and otherwise you can write n as a product of distinct primes. So if it's an even number of distinct primes, it is +1. If it's an odd number, it's a -1. And an equivalent statement is that the partial sums of the Mobius function, which is usually sometimes 0, but usually ±1, is less than or equal to some constant of n to the power 1/2 plus epsilon. And this is very plausible. Because being a prime is something very, very, very random. Looks random. And they're like tossing a coin. An elementary theorem in probability, if you toss a coin n times, a fair coin, heads or tails, chances are that you won't be the central limit theorem within square root of n. So this is very plausible. Yet nobody can prove it. And it's still wide open. Even with 0.9999999, any number less than 1. So this is amazing how little we know. Now, another favorite of mine, and everybody else's, that make you super famous, is the P versus NP problem. To my surprise, some people, not too stupid, believe that P equals NP, but most people don't. And frankly, I'm sure that P is not equal to NP. The usual formulation of the P versus NP problem is via a Turing machine. And I like Turing very much. He's one of my heroes. He's going to be 100 years old in June 23rd. So I really, really like Turing. But I don't like Turing machines. The definition is very tedious and very pedantic. There's another formulation of the P versus NP problems in terms of Boolean circuits. And Boolean circuits, I think, is a beautiful thing. Reminding you, a Boolean function is any combination of variables and the following elementary operations: x and y, x or y, and not x. So if you take any bunch of variables and mix them up, you get a Boolean function. And famously, there is the truth table. You can put x1, x2, x3, if you have, and then 0, 0, 0, and so on. You can construct the truth table, 0s and 1s. And I won't repeat it, but every Boolean function can be realized in terms of these three fundamental gates. So if you have x and y input, this is an AND gate. And then an OR gate like this. So a Boolean circuit looks like something as follows. You have input gates, so you draw n or whatever the number of inputs. True or false, and 0 is false, 1 is true. So here is an example of a Boolean circuit. You have inputs, we call them x1, x2, x3, x4, and then you form a Boolean circuit, either AND or OR. And you keep recursively, and then also not. Blah, blah, blah. And there's one here called the output gate. And this computes the Boolean function. And for every assignment of the 2 to the power n inputs, you have either true or false. Now it's an easy exercise that every Boolean function can be realized in terms of a Boolean circuit. Simply, from the truth table, you have something called disjunctive normal form. For example, here we have, you look at all those that have truths. So x bar, x2 bar, x3, or, so you can canonically write it as disjunctive normal form. And from this you can form a Boolean circuit that computes any function. It's always possible to construct a Boolean circuit that computes any given function. But we mathematicians and computer scientists like to be optimal. We are cheapskates. We'd like to have as few gates as possible. So we'd like to have the minimum number of gates to construct such a thing. Now there are about more than 1,000 so-called NP-hard problems. My favorite is a coloring of a graph. 3 coloring. So a graph is really n people, where every pair of people is a love each other or hate each other. So in this case you have, I don't know, 4 people. Mr. 1, Mr. 2, Mr. 3, Mr. 4. Or Mr. That's an example of a graph. So you have n choose 2 edges, because, and for every edge you either love, for every 2 people, I and J, you either love each other or hate each other. Here, 1 loves 2, 1 loves 4, and so on. Now a coloring of the graph is assigning colors. Red, green, blue, and green. So you have 3 to the power n possible ways to color any given graph. Now a coloring is called legal if any 2 people who love each other joined by an edge have different colors. So there is an algorithm given a graph, an arbitrary graph, whether or not you can 3-color it. Let the computer generate all the 3 to the power n coloring. For each of every one of them, check whether every two people who love each other have different colors. And as soon as you get an example of an edge with two the same color, you put fail. And if you succeeded, yes. But this is exponential time algorithm. Question, can you do it in polynomial time? Nobody knows how to do it. So how to do it rigorously? Algorithms, the usual definition of algorithm, the formal definition is via a Turing machine that I find very tedious and boring. But you can do it in terms of a Boolean circuit. So you can easily write the Boolean function. So now the inputs are x12, x13, so you have n choose 2 inputs. Doesn't matter, it's quadratic, but that's okay. So those are the inputs. So 3 coloring is some concrete Boolean function of n choose 2 variables. We can easily do disjunctive normal form. And you can easily construct a Boolean circuit that computes this specific Boolean function. All you have to do to win the $1 million prize is to prove that any circuit that computes it cannot have polynomial many gates. So it's not possible. The number of gates, so it's accounting problems again. The number of gates in any putative Boolean circuit that has input gates, and choose 2 of them, would have more than polynomial. It's not possible to have a polynomial. So it's a very naive thing you can explain to many people. And this is still wide open, and good luck. So these are the big things. Let me just tell you about something that is not such a long shot. There are lots of famous problems that can make you semi-famous. But before going to the less famous problems, I have to mention some other big guys. The twin prime conjectures that are infinite many twin primes, that's wide open in the Goldbach conjecture. But that's really a long shot. Another famous conjecture that turned out to be false is Euler's. Euler conjecture, the same Euler who disproved Fermat conjectured that it's not possible to have 3 integers, x, y, and z, that if you add up the 4th power, you get w to the power 4. It's not possible. And then, about, I don't know, 10, 15 years ago, a brilliant Harvard mathematician Noam Elkis found a counterexample. And he used fancy stuff, using elliptic curves. But the hindsight, you could have found it, and he suggested a computer search. And the smallest example is due to Roger Fry using computing ideas suggested by Noam Elkis. So this is the famous disproof counterexample. So here's Euler, and conceptually it's completely trivial. And to prove it, you can even prove it, okay, maybe not a calculator, but with Maple takes a second to verify it is true. But even to search it with nowadays, it's still feasible by compute, not brute force completely, but inspired brute force to disprove Euler. So I'm sure there exist examples like this that you can find a counterexample. But in this case, of course, conceptually it's trivial. But if you want to have a hope of proving or disproving things, so here is one way, numerical things. So in one sense, it's trivial, in some sense. But something not so trivial that also conceptually trivial, not computationally. Computationally it's not trivial, even today. Another beautiful counterexample that I love, and unfortunately not many people know about it, so let me tell you, is Hilbert's 17th problem. So obviously, if you have a bunch of polynomials in several variables, for example, x squared minus y plus 1, and you add up the squares, you guarantee to have a positive polynomial, a polynomial that is always positive for any real inputs, x and y. So of course, sum of squares implies positivity. And Hilbert's 70s problem was essentially whether it's true. And in 1966, Theodor Motzkin came up with a counterexample from the book, disproving the famous problem. Before it was, there were other work by, I don't remember whom, much more complicated. But Motzkin's counterexample is so beautiful. It's a one-liner that disproved a famous conjecture, the Hilbert's 70s problem. And here it goes. The following polynomial, according to Motzkin, and I'll tell you in a second what it is not sum of squares. One, you only need two variables. 1 plus x squared y to the power 4 plus x to the power 4 y squared minus 3x squared y squared. First, we have to prove that it's always non-negative for every xy, real numbers. Any ideas how to prove this? That's the first claim, that this polynomial is always positive, no matter what x and y are. Any ideas? I'm very proud of you.
AMGM.
Very good! Who's that? That's right, very good. So, with the AMGM thing. Arithmetic mean is bigger or equal to the geometric mean. And it's the same. Now, it's an exercise I leave to you to prove that it's not a sum of squares. The way you do it is just you just try out. Suppose, of course, it's only of degree 4, so it's easy to guess the form of things. So you have putative, undetermined coefficients, and you can rule out the possibility they can write this as a sum of squares. So that's a beautiful counterexample of a famous problem. So that's one way to develop your skills. Don't just try to prove or disprove things. Look at what already exists. Look at proofs and disproofs of famous open problems and try to learn from it and see how you could have done it yourself. That's how you get good things. Solve problems. That's how you prepare for the qualifying exam. You do problems and look at the answers for Olympia and anything. So, that's my favorite. Another class of favorite things, probably very hard for any specific thing, but you never know, are irrationality. It tells you how little we mathematicians know. We know so little. It's so easy to come up with impossible problems that nobody has any clue how to prove. It's a very easy exercise to prove that the number E is not rational. You know, it goes back to 2,500 years ago to the square root of 2. It's not rational. And nowadays it's not too hard to prove the square root of 2. It's not. It is rational. And this also is not very hard to prove. A little bit hard to prove is that pi is irrational. This was done by Lambert in the mid-18th century. This is easy. Euler, easy. This is not so easy. The stronger statement that pi is transcendental, that pi is not an algebraic number, was famously done by Lindemann in 1882. And this was historically important.